Okay, so we're going to start on section 2 of chapter 5, and the title of it is simply area. That's just the title of it, okay? Alright, so pretend you have f of x equals to negative x squared plus 5, and I wanted you to find the area under f of x and the x-axis between 0 and 2. Okay? So you have f of x equals negative x squared plus 5. I want you to find the area under f of x and the x-axis between 0 and 2. So first, what I recommend you do is sketch what this looks like. Agreed? Okay. You don't need a calculator for this. You should know how to graph negative x squared plus 5. Hopefully. It is a parabola that has been shifted up 5 units and it's been reflected over the x-axis. Agreed? So let's go by ones. 1, 2, 3, 4, 5. So that should be there, right? And then where else? Let's see. If I plug in 1, I should be at there. So this looks something like that. Agreed? Yes? No? Maybe? Correct? It's not perfect. It doesn't have to be perfect. But here's what we know. I want you to find the area under the curve between 0 and 2. So if this is 1, that's 2. In other words, I'm asking you to find this area. Agreed? Okay. That doesn't look like any shape. Now, there's a couple things that I've seen students try to do. They're like, well, I can make a square here, and then another one here, and then another one here, and then that's how they approximate, just breaking into shapes that they know. Agreed? Well, we can do something similar, and we can use rectangles. So I'm going to go to the side here, and this is not going to be exact once again, so pretend this is the same graph that we have there. You can actually draw rectangles of equal widths. So for example, I can say that I can draw a triangle that's from here to here. Let me use a different color. And then just go up and then draw a rectangle there. Cool? And then I can do the same width right here, and then it would draw a rectangle there. Agreed? And then I can draw another rectangle here and there. Cool? Now, if you find the area of the rectangles, you're going to get this, you're going to get that, you're going to get that, but you're not going to get what I left blank. So it's going to be an approximation. Well, how could I get a better approximation? Any thoughts? What's that? I agree. What if I take the exact same diagram there, but I make the rectangles half of what they was, so that goes from there to there, from here to here, that one matches, from here to here, from here to here, from here to there, and now all of a sudden I'm covering a little bit more than I was before. Agreed? So if I wanted a better approximation, what could you do? Make even smaller rectangles. The key here is that they're all going to be the same width. Okay? Do we all understand that? So here's what we're going to do with this. I'm going to improve the sketch of this, and I'm going to make it a little bigger so that we can see the rectangles on your notes. Okay? So here's what we know for sure. I'm going to make my scale a little bigger, so I'm going to say every 2 is 1, 2, 3, 4, 5. Okay? And then I'm going to say, just for space purpose on the y-axis, I'm just going to go by ones. Are you okay with that? Alright, so I'm actually going to get a better sketch. So if we know that we got to be at 5, right? If you plug in 1, what's 1 squared? 1 times negative, it's negative 1. 5 minus 1 is 4. Agreed? If I plug in, I don't know, 2 squared is, times the negative is negative 4 plus 5 is 1. Agreed? So at 2 you're going to be at 1. Correct? So this sketch is going to look something like that. Right? I'm interested to go from 0 to 2. You guys with me? That's what the problem was asking. What do you guys suggest I could do? Or where could I start to make this simple for us and then we can improve it? How can we find a good approximation of the area? We need to find rectangles of equal length. Agreed? What do you guys suggest that I start with? How many rectangles would be a good idea? For now, since we're just starting. 4? No, not 75. I would say 4 rectangles because I can draw rectangles here to there, right? Here to there, from here to there, from here to there. Agreed? From 0 to 2. Now here's my question. From here to here, we're going to call it delta x. It's a change in x. Agreed? Now here's my question to you. How can I find what delta x is? Well, I know that you can visually see it, and you should know that it's going to be 0.5. Agreed? But how can I tell what's delta x algebraically? Well, this is your last point, right? 2 minus 0. Agreed? That's your first point. How many rectangles did you use? So now, we are going to use summations. We talked about summations in pre-cal last year. Do you guys remember this symbol? What is that symbol? What letter is that? Sigma, and it stands that we need to do a summation. Agreed? Okay. Now, let's talk about a summation. We need a summation starting from 1 to 4. I'll explain to you what that means here in just a second. All right. If we were to do this rectangle by rectangle, how would you find the area of this very first rectangle right here? What do you guys think? How would I find the area of this rectangle right here? Well, the area of a rectangle is length times width, right? We know that from here to here is delta x, right? We need to multiply that by how tall this thing is, right? How can you figure out how tall that is? Well, how can I find out what this point right here is? F of 0.5. Agreed? That will get you this height right here. Do you guys with me? That will get you that rectangle. And then you need to find this rectangle. Agreed? How would I find the area of that rectangle? Delta x times what? F of 1 plus this rectangle, which is delta x times f of 1.5, right? Plus this rectangle, which is delta x times f of 2. Agreed? I need to come up with a formula so that I don't have to write all these terms. So could I then say the summation from 1 to 4 is, can you notice that you can factor out a delta x from here, right? It's technically delta x times f of what? What's up? Say it one more time. I? Say it. I times delta x. Well, here's the thing. If you put in 1, you're going to get this one, right? If you plug in 2, you're going to get this one. I over 2. Do you guys agree? Because if I plug in 1, I get 1/2. If I plug in 2, I get 1. If I plug in 3, I get 1/2. If I plug in 4, I get 2. Do you guys see that? This would be the formula to finding this. Agreed? Now, can we actually find the area? Well, does anyone have their calculator to help me out? Yes? Ready? Okay, so what do we know delta x is? 0.5. Agreed? Times, I need you to find out what f of 0.5 is, f of 1, f of 1.5, etc., etc. So just go to the table, go to negative x squared plus 5, and just tell me what the values are. Or just plug it in your calculator. Do you guys remember how to plug it into your calculator? Summations? No? Alright, let me pull out my calculator so it's on the video. Oh, that's great. I left my calculator in my office. Can I borrow someone's calculator? Oh. Alright, summations. Who remembers how to do a summation in the calculator? Where do I go? Math? Then what? Sum. Number.
Or you can go to alpha too.
Where's sum? It's in math. There you go. You can go there, or if you do alpha, I think it's window. It's the second option. You guys see that? So then I would say x starting at 1 going to 4 of, well, delta x I would actually input 0.5, right? So 0.5 times x over 2. Agreed? Well, we actually need to do f of x over 2. So we need to put the actual function, which was negative x over 2, right? Squared plus 5. Right? Oh, delete. Second insert squared plus 5. Agreed? 6.25? Awesome. Okay, get rid of that. So I'm going to say that this is approximately, well, this is exactly 6.25 units square. So we can say that the area is approximately 6.25 units square. How could I get a better approximation? More rectangles. Agreed? On your homework, it's going to tell you how many rectangles to use. Cool? So just for time's sake, are we okay with the process? We're good? Alright. We can draw some conclusions from here, though. Okay? Because there's another way we can use rectangles. You ready? What if I have the exact same problem? So it was f of x equals to negative x squared plus 5. And I still want the area above the x-axis and between 0 and 2. Okay? So I have the same graph here. That's 1, that's 2, that's 3. 1, 2, 3, 4, 5. Okay? Let's pretend we're still going to use 4 rectangles. You guys with me? But this time, what if I do this? Are they the same width? So what would you say delta x is? 2 minus 0 over 4.5. Agreed? And this would be delta x. You guys with me? Okay. What's the difference between what I did on this sketch versus what I did on the other sketch? I went outside of it, right? So I'm going to get more than it actually is, correct? Let me go back to the other sketch real quickly, okay? On this sketch, I drew my rectangles by drawing my height from here up to the curve. So from the right, this is known as a right-ended sum. You guys see that? I went to the right of the rectangle and I went up. Okay? In this case, look at where I started. I went here and then I went up to the curve. Then I drew the parallel to the x-axis and I went down. Up to the curve, parallel, down. Up to the curve, parallel, down. Up to the curve, parallel, down. Cool? So this is a left-handed, right? Okay. Another name that you might see, and you're probably going to see this one on your book, this is also known as an upper sum. And the other one, can you kind of guess what it's called? A lower sum. Okay? That's the two names that you might run into. Cool? Alright. After this, the process is exactly the same. You need to find the sum of each one of those rectangles. Okay? So here's my question to you. If we want to find the sum of this first rectangle, what will we do? So area is approximately delta x times what? Very good. F of 0. Do you guys understand why it would be f of 0? Does anyone not understand why it would be f of 0? I need to know what that point is, right? So I would have to plug in f of 0 to figure out, and that's going to give me this height, right? Plus delta x times f of this value now, which is 0.5. Plus delta x times f of 1, right? Plus delta x times f of 1.5. And that takes care of 1, 2, 3, 4 rectangles. Agreed? Alright, how can I come up with a formula so I can just plug it in the calculator the way we did? The area is going to be approximately the sum of x. Where are we starting this time? 0, and we're going to go to 3. Very good. Do you remember how we came into this problem last year where you're like, well, how do I know when we start with 0 and how do we know when we start with 4? I mean with 1, right? It all depends on your problem. This one we're starting at 0, that's why I want my index to start at 0. Okay? So then it's going to be delta x times f of what? Would it be this exact same formula? So delta x divided by 2, or x divided by 2, I'm sorry, right? Right? Because if I plug in 0, 0 divided by 2 is 0. If I plug in 1 divided by 2 is 0.5. 2 divided by 2, 1. 3 divided by 2, 1.5. So do you guys see how we can use the exact same formula, but we had to change the index in order to make it work for this one? So now, if I want to figure out what this is the same thing as saying the summation from 0 to 3 of delta x times negative x over 2 squared plus 5. Agreed? So I'm going to go back to my calculator, and I'm going to just retype that entire thing, but all I'm going to do is switch the index. You guys okay with that? So I'm going to go to 3, and I'm going to start at 0. And I'm going to hit enter, and I get 8.25. So you would say then that the area is approximately 8.25 units squared. Agreed? That's if I go with an upper sum. You guys with me? So then can we then make a conclusion based on what we got from our lower sum and our upper sum? Therefore, the area has to be less than 8.25. Agreed? But it has to be greater than what? 6.25. Do we understand why? This one we were not actually completing the entire curve, and this one we went over the curve. So it has to be between there. Would you say that that's a very close approximation? In my opinion, no. There's too much of a difference between this. Agreed? We could have made smaller rectangles, and we can then start to decrease and make the difference between these numbers become smaller and smaller and smaller. Agreed? Yes, sir.
Wouldn't that be incorrect because you still have that small bit at the end?
No, because we were going from 0 to 2, remember? So this, I wasn't interested on this area. You see what I'm saying? Because the instructions said between 0 and 2. So I'm only interested from here to here, going up. Good observation, though. Okay? Questions, guys? Are we okay? Lower sum, upper sum. Well, there's 2 more ways. You ready? All right. There's something called the midpoint rule. Okay? So we're going to rule. Pretend that you have f of x equals sine of x, and I want you to find the area between 0 and pi. Okay? I want you to find the area between 0 and pi. All right. If I sketch this out, I'm going to say that this is 1, that's 2, and I'm going to say that's pi, 8 spaces in, so that means every 2 spaces is pi over 4. You guys with me? You don't have to draw that way, you can, that's just the scale I chose, okay? Well, here's what we know. Between 0 and pi, the graph of sine, what's the sine of 0? 0. What's the sine of pi over 2? 1. And what's the sine of pi? 0. So this thing looks something like that. Agreed? Okay. We're going to use 4 rectangles. You guys with me? We're going to use 4 rectangles. So if we use 4 rectangles, do you guys agree that it's going to go up here, 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 and there, right? Now, we're going to use something called a midpoint. So let me ask you, from here to here, what's the midpoint? Pi over 8. Agreed? That's how high you're going to go, and then you're going to draw your parallel. Do you guys see that? Alright, let me show you one more time. So what's the midpoint between pi over 4 and pi over 2? 3 pi over 8. So you're going to go up to that point right there on the curve, and then you're going to draw your rectangle. Cool? And then halfway between here and here is going to be 5 pi over 8. So I'm going to go up to here. And then halfway here is going to be 7 pi over 8 up to there on the curve. And that's my 4 rectangles. Okay? What's the difference with this one versus the upper sum and the lower sum? It's like part of it is on the outside and part of it is on the inside. Do you think this is going to give us a better approximation than the other two? Could be. We'll see. Okay. Alright, so now we have what we need. We have our sketch. Now we need to find the sum. So what would you say the approximate sum is? Alright. What's your delta x? Well, delta x, remember, is going to be this right here, from here to here, right? It's fairly easy to see visibly that it is pi over 4, right? But how would you figure this out algebraically? Pi minus, where did you start? 0, and how many rectangles do you have? Pi over 4. Agreed? So then, if I wanted to find the area of this small rectangle right here, how would I find it? Length times width, so pi over 4 times, I need to know what this height is. How can I figure that out? Good. F of pi over 8. Agreed? Do we understand why it's pi over 8 and not pi over 4? Good. Plus pi over 4 times f of 3 pi over 8. And that would give us this rectangle right here. Agreed? Plus pi over 4 times f of 5 pi over 8. Plus pi over 4 times f of 7 pi over 8. Yes? And that would give us all this area right here. Agreed? Okay. How can I reduce this to a formula so that I can use a calculator? Any thoughts? It's definitely going to be pi over 4 times something, right? F of what? What do you guys think? Alright, since none of you could come up with it, we would say that it's 2 pi x plus pi over 8. I'm just kidding. I'm going to give credit to Saf for this. And we're going to start at, where did you say, Saf? And go to 3? Well, we need, so 3 times 2, right, gives you the 6, so the 3. You guys with? We cool? Alright, so at this point, what are you going to plug in the calculator? X equals 0 to 3 pi over 4 of, well, what is f? Sine, right? So we're going to say sine of 2 pi x plus pi over 8. Cool? And we have to make sure that we are in what mode? Radian. Okay, so the summation from 0 to 3 of pi over 4 times sine of 2 pi x plus pi over 8. We good with that? What? Did I not type something? Pi over 4. Thought I did. What are you doing? Clear. I'm gonna have to retype it. X 0 to 3 of pi over 4 times sine of 2 pi x plus pi over 8. Why are we getting an error? Why is this not working? That's 0. That's pi over 8. Why is this not working? Sine. So, like, get rid of what parentheses? Oh, why is all that there? So I need to get rid of those two. So just like that. Alright, bingo. Just a whole bunch of extra parentheses. Approximately 2.052 units squared. Cool? If you were not able to get here, could you have, actually, it wasn't too bad. It was 4 different rectangles. Could you have find the area of each one of rectangles and then added them together on your own? Yes? Worst case scenario, if you ever get stuck, do one by one. Okay? Questions? We're good? Which takes us to the very last rule, which is called the Trapezoidal Rule. Alright, so we're going to use the Trapezoidal Rule. We're going to do the exact same thing we've been doing. We're going to find the area of under the curve of this function between 1 and 6 and above the x-axis. Okay? So if we graph this, alright, so if I plug in, so I'm going to start at 1. So if I plug in 1, 1 minus 1 is 0, square root of 0 is 0. So I'm going to say that this is, let's go by 1, 2, 3, 5, 6. So 1, 0, right? If I plug in 5, 5 minus 1 is 4. So something like, oh, that's terrible, I didn't even go through the points. Something like that. Agreed? Alright, so then, if I want to find the area between 1 and 6, I'm looking for an approximation of that area. Agreed? Okay. Let's use 5 rectangles to keep our life simple. well, not rectangles, we're going to use 5 trapezoids since we're going to use the trapezoidal rule. So let me show you what I mean by that, okay? So we're going to use 5 trapezoids of same height. Now, just a reminder of what a trapezoid is. Do you guys remember what a trapezoid looks like? Okay, there's a couple of trapezoids. A trapezoid could look like that, or like that. You guys recall those, right? Which one would probably make more sense for this? The top one, okay? So here's what we're going to use. We know that a trapezoid, this is a base, let's call that a base 1, that's base 2, and then that's the height. Agreed? How do you find the area of a trapezoid? Area of a trapezoid equals base 1 plus base 2 over 2 times the height. Do you guys remember that? Okay. So here's what we know. If I want to get 5 trapezoids with the same height, let me show you how we can achieve that. I'm going to use the exact same method as we did with the rectangles. I'm going to go from here to here, from here to there, from here to there, and from here to there. But now, check this out. What if I go from here to there, from here to there, from here to there, there, and there? Do you guys notice that the space that's left out is very minimal? So would you say that if we use trapezoids, our approximations are going to be a lot more closer than using rectangles? Now, for those of you that are having trouble seeing where the trapezoid is, I'm going to turn the paper.
Whoa.
Base 1, base 2, height. Base 1, base 2, height, and so on. What used to be our delta x, our width for our rectangles, our delta x with the trapezoids happens to be the height. Agreed? Okay, so we need to find the sum of this. So the approximate sum is going to be equal to, well, we need to find what delta x is. Delta x. Alright, so if I go up here, delta x is equal to what, guys? 6 minus 1 divided by 1, 2, 3, 5, which is 1. Agreed? Okay, so then if I want to find the area of each one of these trapezoids, so that would be delta x times what? Good. If I want to find out the first base, so like for this one, it actually happened to be a rectangle. Do you guys agree? But I can still treat it as a trapezoid. I could say that to find this point right here, that's f of 1. Plus, how would I find this? Divided by 2. Do you guys see how this is the exact same thing as that? H represents delta x. Base 1 is represented by the f1. Base 2 is represented by the f2. And then there's a 2, right? Plus delta x times. Now we're looking at this trapezoid here. F of 2 plus f of 3 divided by 2. Agreed? Plus delta x times f of 3 plus f of 4 divided by 2 plus delta x times f of 4 plus f of 5 divided by 2. And where are we at? So 1, 2, 3, 4, 1, 2, 3, 4. So we got one more. Plus delta x times f of 5 plus f of 6 divided by 2. And that's going to give me the approximate sum of under that curve from 1 to 6. Alright, so we can then say that the approximate sum, I'm noticing that all of this have in common a delta x and a 2 on the denominator. So I could factor out a delta x over. If I do that, then I would just be left with f of 1 plus f of 2 plus f of 2 plus f of 3 plus f of 3 plus f of 4 plus f of 4 plus f of 5 plus f of 5 plus f of 6. Agreed? So then I could say that is f of 1 plus 2f of 2 plus 2f of 3 plus 2f of 4 plus 2f of 5 plus f of 6. You guys with me? So then the approximate sum would then be, well, what is delta x? 1/2 times. And we can figure this out real quickly. So what is f of 1? Well, if you plug in 1 into the function, 1 minus 1 is 0. The square root of 0 is 0. Plus, if you plug in 2, 2 minus 1 is 1. The square root of 1 is 1. Times 2, 2. Plus, 3 minus 1 is 2. Square root of 2 is square root of 2, so 2 root 2. Right? Plus, f of 4. 4 minus 1 is 3, so square root of 3, so 2 root 3. 5. 5 minus 1 is 4. Square root of 4 is 2, times 2 is 4. And lastly, square root of 6. I mean 5. My mistake, not 6. Because 6 minus 1 is 5. You guys with me? I went ahead and plugged that in the calculator before class. And what I got was approximately 7.26 units squared. Cool? Trapezoidal rule. Before I finish the video, I just want to mention this. Next class, we're going to learn how we can go away from using these types of techniques, except for the trapezoidal rule. The trapezoidal rule, there's a reason for it, because if we really think about it, of all the rules that we saw today, would you say this one's the one that's going to get us the closest? Because it's the less space in between the curve and the actual trapezoid. There are going to be, we're going to be using antiderivatives, which I'll tell you what that is next class, to go away from using rectangles. However, there is going to be certain situations in which antiderivatives will not work, and you're going to have to use the trapezoidal rule. Cool? And that's what in the future. Alright, that's all I got for y'all today. Homework, I'm actually about to put it on the hub.